maybe we already partially covered it last time. So when the code has successfully completed, we do have several panels popping up, and the meaning of these panels are expectation values of position, the width, and the probability distribution. So we need to overview how it is done, just in case if we need to compute and present observables that are not automatically printed. So to manipulate and practice the sandwich procedure. So some an observable as function time. So last time we have already covered the this distribution, right? But I'll better remind it because we have a little better attendance today, so that it doesn't go unnoticed. So if I close all the things just to have it healthy, and then so the main loop that propagates with packet forward in time starts in this 164 and goes until is symbolized by this little line. And when at the very close to this line, we do have the accumulation of the probability distribution to the next time slice. So after the code is done, this command is this variable is printed, is plotted to the screen. So in addition, let's look onto the expectation value of position. So if our operator is just position, it doesn't change wave function. So we can do wave function absolute value squared, which is probability variable. And then we have variable x, which spans over the whole area of definition. So if we, with this little period, if we multiply it element by element and then add together, it will be expectation value of position for a given moment of time, for the present value of the loop variable. But later on, we need to plot the trajectory, how this expectation value changes over time. And in order to do so, one does need the accumulate several values into an array, and it can be done either with this semicolon, then it creates the raw vector, or one can write it this way. Then it will accumulate in the column, right? So it will be the data object that is incremented each time we come through the through this point in the code. So I'll probably open another device and show the same thing. It just will give better functionality, but please try to do the following exercise, and I'll watch what happens. So mesh s. What was the name of variable? S or S3? Okay. So try to do mesh S3 and in a new window, and then and rotate it, and then after, please try to do the AVGS3 in. And see what happens. So I will visit everyone one-to-one and see if you have it up and running, and then we'll go to the next stage. AVGS. So whatever you see in line 210. Okay, and the previous one for, can you do it in the separate window, just to type, if you want new window, you can type figure. And then it opens a new panel for drawing. Not plot, do mesh S3. Okay, yeah, good. you're running different version of the code, right? For harmonic oscillator, probably. Yeah, you see here HO. Well, did you run the code completely from the beginning to the end?
Yeah, I did. It gave me this error.
Wait. Can I?
Yes.
So when?
Oh, just
Is your code here?
yeah.
Comments. So it asks press any key. Did you do it?
And that gives me that error.
No. There is no. Interesting. So it works, right?
Yeah.
And then if you do put AV, so it gives straight line. So if you were not playing with the code last time and you have original unchanged version, it is tailored to describe electron in free space, which moves on a straight line, right? So expectation value of position goes on a straight line. So let me invite, I'll stop share. Let me invite everyone one by one to share screen and show if you can operate images. Ellison, would you please share screen?
Yep.
So everyone is cool. Oh, yeah, let me make. Okay.
And then run this.
No, wait. No. Are you sharing only one window or the whole display?
Oh, here, let me share it all.
It should be the whole display, otherwise it will be a little problematic.
Let's see. How do I share the whole thing again?
When you do share screen, when you
Yep.
share screen, it gives you a list of all windows you have opened. But the first thing is an option to share the whole screen or whole display.
Oh, there it is. Can you see it now?
Okay. Now, you have several windows open. If you do Alt tab, alternative tab, you are two buttons at once, alternative and tabular.
Like,
then you switch between different windows. So please navigate to the figure from MATLAB, either by pushing Alt tab several times, or if it doesn't help, in the bottom front panel. Yes.
there we go.
So here is figure 4. Can you bring up figure 1, figure 2, or you can erase all figures and then do a new. So maybe close this one. It's not of a big value. Just close this, bring back this figure 4, bring it to the front. Now close it by red circle in the
Yeah, sorry, the thing is covering it. How do I move this?
top left of the figure 4. There is a red circle with a little X in the center.
Yeah, I've just the top bar on when I share my screen is covering the red button.
Okay.
Let's see. There we go. Okay.
Okay, and for the also close this one. Yes, and close this one, and close this one.
Okay.
Okay, now everything is clean. Now type figure once again in the command line. Figure, enter, and now in the command line type mesh, MESH, open bracket, open parenthesis S3, lowercase S3, close parenthesis,
Enter.
enter. Okay, so you have this probability distribution, and let's move your mouse, slowly move it up, slowly. And you see on the top right, there is a kind of vanishing menu with show,
Yep.
click right here for rotate 3D. Click there once, and now try to rotate this image. Okay, yeah, I think it is good. Now let's go to the command window and type plot, open bracket, AVGS 3, close the bracket. So it is a straight line, but it's on the X, it is time steps. On the Y, it is grid points of X. But only in this case, it is straight line. In all other problems, it will be something different. Okay,
Okay.
you can stop sharing, and let's check who is next. Sibel, would you like to share screen?
Yep. Okay. Hold on. Am I sharing my screen?
Yes, I see only one window. Let's
Okay, hold on.
share the whole display.
Okay, hold on. Can you share? Screen. Okay.
Stop sharing first, and then
Better.
okay. So, but now you're let's bring your command line up.
Okay.
Yes, it is here. And now let's arrow up once again. Arrow up twice in the command line.
Arrow.
Type mesh S3, or you can just arrow up twice.
Okay. Hold on.
Arrow up. No, it doesn't work.
No.
And just retype mesh S3.
Okay. Okay. Here.
Okay, yeah, it's great. Everything
Mhm.
works. Now you can sharing.
And then.
Everything, yeah, everything is great. Joshua, so Sibel, please stop sharing.
Okay.
Joshua, would you please share?
All right. Just need to get the invite. It says host disabled participants screen sharing. So
Okay, let's fix it. It will be really make co-host. Yes. Now you should be able. Professor Krzyzewski, I'm teaching the class right now.
All right.
Yeah, please call other time. Okay, yeah, thank you, bye. And did you, yes, okay, you're doing correct.
Uh,
Busy, it shows busy, okay.
yeah.
What, okay. And now you can either close all these figures or open a new figure. You can close, there are 1, 2, 3, 4 figures.
Yeah.
Close,
Run.
close.
Run.
Now type in the command line that was open just a command window. Type same as everyone was doing. Mesh, open bracket.
Okay. Mesh. Or bracket.
Yes, 3. Not rectangular bracket, but regular round bracket.
Like this.
Yeah. No, not
Oh,
curly.
can I the parentheses?
Simplest possible.
Wait, that. I'm sorry, I'm a bit confused, but is this
And now type
Yeah,
S,
or-
C, lowercase.
okay? So S lowercase and then 3.
Close bracket. Okay, and try to rotate it. Yeah, click rotate 3D and in this. Okay, yeah, it works very well. Great. Now in the command window, type plot AVGS 3.
AVGS3.
Yes.
Right.
Okay, perfect. It works. So you can stop sharing. Everything works at your
All
side.
right.
Let's just, so please stop sharing. And Lola, would you please share your screen? Okay, it looks like you're sharing on the command window. Maybe stop and share again the.
This one?
Okay, yeah, great. And
Okay.
can you now type that it will convert into just a line? Type plot, open bracket, AVGS3. Yeah,
Yeah.
no space, no space before bracket. Okay, enter. And let's click on this MATLAB figure window just by mouse. Okay, excellent. I think we all are on the same page.
Okay.
So yeah, excellent. Please stop sharing. So I do have a question which maybe we do not have time to individually ask everyone, but maybe you have noticed that when we were doing the plot AVGS3, some of you got straight line, absolutely straight. And some of you got line going almost to the top, then dropping to the bottom and then raising again. Please tell or just show sign if you can explain this difference. Nate? Yes, no?
I'm trying to remember what I had missed. Mine was not just straight.
So who is Adam is not at the lab, but he is assigned to describe how to change initial conditions. And maybe we'll split this section, this question with Lola. So let's go. Maybe we delay everything a little bit, but later on, if we get basics, it will be quicker. I'm ready to talk to explain myself, but let's check. Wait, can you explain the difference? Joe? Okay. Who else? Ellison, Sibel, Josh, or Lola, any of you can raise hand and explain what is going on, why the AVGS3 was slightly different for different class attendees, or you prefer my explanation? No idea. Okay, yeah, thank you. Thank you. So let's go to the beginning of the code. So I'm scrolling at the beginning, and bless you. So if you were here last week, we went over it, but if your schedule didn't allow, then it will be a kind of new experience. So at the very beginning of the code, we set up initial parameters, and X naught is position where we start center of the wave packet. P naught is a momentum. Right now, the momentum is set up quite slow, so it doesn't pass through the whole simulation cell. If we multiply it maybe by 3 times, not 32, just 3, save and run once again. So please try doing, not watching what I'm doing, but try to do it yourself.
Mine was at 3, so I
Okay. So Nate, what is expected before I run? Otherwise, you lose the intrigue.
Is it because it goes across and starts, it goes all the way to the end and then starts over again? Or-
Excellent, thank you. Wait, Joe, is it clear or not? Yes? So let's run it. I'm running the same code, but you see it goes much quicker. And it disappears through right border and reappears through the left one. So, and after the code is finished running, we see this image when the X average position, average coordinate increases and drops, and then it increases again because it passes through periodic boundary conditions. So please do this this little exercise, and if you plot probability distribution, you see instead of 1 stripe there are 2. So it starts at 30, goes forward, disappears, and then reappears again. Okay. So I'm putting 1.25 as its better demonstration. So I'm returning to the observables and expectation values. So we did consider expectation value of position, which is oversimplified special case. Let's look onto the momentum. Let's check if you have it here. Yes. So let me attract your attention to the lines 222 and 223. So right now we are replacing operator A with P2 matrix that corresponds to momentum operator defined by method number 2. So we are limited in time. If you missed lab number 7, previous lab, please consider to watch it. There are some, even if definition of momentum is only the responsibility of Wyatt, it is kind of important that we all get through basic ideas. Right now, just there is no time. So instead of A, we have P2. Instead of psi, we have psi2 conjugated. Instead of psi, we have psi2. And instead of this integration, we just have the instead of this integration, we replace integration by row by matrix by column rule, right? And then as a result, it gives a number. So you'll get expectation value of momentum at time t, right? So let's illustrate what we see here by the following checks, inspections. So main thing is to do plot. So which variable is expectation value of A is AP. So plot AP. If you type it, there is a chance that you'll get an error or you'll get some very noisy figure. Then I would try plot real AP. No, it will not. It will be just 1 point. Let me attract your attention to line 227. This is needed to create the sequence of data in one array that would correspond to trajectory of this time-dependent expectation values. So plot not AP but AVEP, and AV real part plot imaginary AVEP. So generally, the variables in MATLAB are complex, and even if it is purely real, the really complex number, and the plotting subroutine can be confused if there are both real and imaginary part, which one to plot. And if you mandate to plot either only real or only imaginary, the result will be much more reasonable. And after you do these 3 checks, another one will be to do mesh imaginary P2. So this last check deals not with our today's goals, but with main subject of that Wyatt will present on November 5th, but we all should realize what it is. So how the operators are represented in matrix form. So please try doing this little exercise, and in a minute I will approach everyone and have a look.
not liking the mesh P2. It's
But did you succeed to do previous ones? Real?
real.
Okay. So how do you interpret the fact that real is not changing? Is there any reason that makes momentum to be changed if it is a free space without potential? Okay, so the momentum is constant of motion. Uh-huh. So it is, and please bring it back once again. How does it correlate to the value that we set up at the line 5 P naught? Very, very beginning. It's something different, but very close because of some numerical error. So basically, it should be what we set up. Okay. Anything else you want to show?
If you plot them both together, then it's like this.
Yes, but it is 10 to the minus 16, which is almost 0. Okay, good. Thank you. Yeah, this is imaginary, this is real, and it doesn't change over time or change is negligible because no potential. Good. So let me ask Alison, would you like to share a screen? Just briefly.
Yep.
Thank you.
All right.
Okay.
So there's the
So it is
imaginary.
imaginary, right?
Yep.
You see y-axis, it shows that it is multiplied by 10 to the minus 17. Do you see it?
Yep.
So it means it is as good as 0.
Okay.
Okay. And if you do real,
I guess I just call it.
arrow, yeah, arrow up saves. Okay. 0.31. So it looks like you were changing the initial, the momentum is also not changing much. You see all these numbers along y-axis
Yeah.
are the same up to like 5th digit.
Yeah.
What if you type P naught in the command window? Type P uppercase, and not lowercase. Backspace, uppercase P, lowercase not, N-O-T. Enter. So you set initial value 0.25 and measured value of momentum is like 20% bigger, but it doesn't, it changes, almost doesn't change because potential is 0.
Okay.
Okay. Did you try to mesh, to plot the, yeah, mesh, open bracket, imaginary, it's better do imaginary, close bracket, P2. No, not close, open one more bracket, sorry. P2, 2, close bracket once and twice. Okay, so let's check what is wrong. Maybe PX2 and uppercase. Imaginary, uppercase P,
X2.
X2, close bracket, enter. Let's open the line in the code, line 222. What is written there? Just move this figure a little aside.
Yeah.
So PX. Okay, let's edit the line.
This one?
Yeah, let's go to the command window once again. And instead of typing, just do arrow up to bring last sentence. And then remove 2, make just PX. Enter. Okay. So do you have any, and you can do this 3-dimensional rotation. A beautiful figure. How do you interpret it?
It's a lot. It's pretty.
So basically, defining and understanding this figure was the main subject of the meeting a week ago.
Yep.
Did you have a chance to watch it? or not yet?
Yeah, I did.
Huh?
I was in lab. Yep.
You was here last.
Yep.
Okay. So how do you interpret this image?
Basically just it's 3D because we've got all of our
But what does it show?
it shows I'm blanking from last week.
Hmm?
I am sorry, I'm forgetting from last week what it
So it's a momentum operator. So it's matrix from
okay.
operator in finite differences. We all are waiting November 5th to hear how Wyatt will explain it to us. Okay, and you see that it has both positive and negative because we subtract near values or nearby values of wave function.
All right.
Okay, so the homework which will be due on the Monday after your presentations, we'll have some questions about it. So try to either look back on previous lab or just prepare to be very attentive when Wyatt is delivering material. Okay, Alison, you may stop sharing. You may stop sharing.
Yeah, I don't know. Let's see.
Stop.
I'm missing my bar.
Let's check maybe. Let's check if I can stop your. I do not see it. Stop participants sharing. Okay, I think I have a button to stop your sharing.
Oh yeah.
Okay, I did. Yeah, thank you. So, Sibel, would you please share your screen? Okay, great. And would you please bring this reel of P2? Imaginary, and what is the figure? So this is imaginary, so it is 10 to the minus 16. And if you do real, okay. So are you happy with this? Does it make sense?
Yes,
Maybe-
it does.
Okay.
Sorry, I was trying to find the buttons.
Okay, everything is great. Then you can stop sharing. Okay, thank you. Joshua, would you please share screen? Okay. And show what is going, which figures can you show? Yes. Can you explain what is being shown by your own words? Or at least,
I think it's something to do with the momentum operator.
so why the imaginary part is so big? And if you do real, probably it will show something like 10 to the minus 17.
Sorry, I'm just blanking out.
So definition of momentum is includes imaginary unit times Planck constant times derivative over space, right?
Yep.
So the matrix itself must be imaginary.
Yep.
Can you make connection between this figure and definition of derivative in finite differences, or you think it is too challenging?
Yeah. Yeah, I'm just trying to think, but I'm having a hard time.
Okay,
Yeah, sorry
but
about that.
keep it on the back burner this idea that how to connect this figure with definition of derivative in finite differences. Would you please? And here is a little hint: instead of typing things, if you repeat something, you can just do arrow up. It will repeat stuff that you were before. So plot real. Okay.
Yeah.
Okay. Yeah, so it doesn't change over time or changes negligible. And if you do imaginary part,
Yeah.
just arrow up, and then it will repeat this last saying yes. And now you can
Yeah.
edit. So the amplitude is really small because the axis shows 10 to the minus 16. So momentum is real. Okay, everything is great. You can stop sharing. Lola, would you please share your screen?
Yeah, sure.
Thank you. Okay. Yes. And would you please make the image of the momentum as function of time?
How do I do that?
In the command line, type same as like plot.
Oh, gotcha.
Open. If you share the whole window,
Okay.
it would be a little easier.
Do you see it now?
Yes, yes. Plot, open bracket, real AVP. Bracket, another bracket, open bracket, real AV uppercase P, close bracket, enter. Okay, so you see it, it's basically a constant. The change is in like 10th digit, right?
Mm-hmm.
It is real. Okay, yeah, that's great. You can stop sharing.
All right.
So maybe share from the other device. Oh no, this one. So what is our oh, okay, we're not done yet with expectation values. There is another thing that we may want to focus on. Let me stop sharing and just focus on the blackboard. Suppose our wave function changes from very narrow at initial time to very like expanded in the final time. How can we summarize the thickness or width of the wave function in one number? Any ideas? Like, what do you do? I know that Sibel is doing experimental research, right?
Yeah.
So if the spectral line is, you need to report that in some spectrums there is a very thin line or very thick line. How do you verbally describe what is their difference?
Well,
There is, yes, keep going.
so for me, it's based on the how broad the absorbance of the wave of absorbance.
Yeah, there is an abbreviation that I never can memorize because I'm not experimentalist, but it is 4 letters and the first letter is F, like which means width at a half height. Did you ever saw something like that? Please show yes or no. Or no, okay. So so example number 1, example number 2. We want to measure the width. Basically measure from here to there, right? At the half from here to there. And we want an algorithm that converts the numerical representation of the probability distribution of wave function into this number. If we do have pen and paper solution, if you know that it is Gaussian wave function, we just look E minus x squared divided by sigma. We look for the value of the sigma parameter, right? But if we do not have the equation, if it is something that comes up from numerical distribution, how do we find this width? Or by other words, it is uncertainty, right? How much position is uncertain? Any ideas? Lola, do you have any ideas to share?
I didn't get your question, sorry.
Please define what is standard deviation. If possible. If not, it's fine.
Standard deviation?
Huh?
Deviation from, I don't know. Deviation from the mean, that's what I know.
Exactly, deviation from mean. Anyone else is happy with the word standard deviation? Ooh, I found way to your brain and hearts. Okay, what we are looking is a standard deviation. We need an equation for standard deviation. If the center of this wave function is our expectation value of position, right? And this width, we can call it by the word sigma. And we do know our wave function psi. How to extract this psi from the numerical wave function? If it would be analytical wave function, we would just take derivative or something like that and extract it up front. But here, there is a trick, which I'm sure you all know. It just vanishes from the active random access memory. So if we know the center of the distribution, then we have a point on this distribution and look how far it is from the center. Then this is a measure of deviation from center. But deviation from center can be either positive or negative. So if you would multiply this difference by wave function and wave function square, the result will be 0, right? But if we put power 2 here, it will be always positive. And then we can use it as definition, or we can define it as a square and then x square root. But basically, whatever, if you put deviation from expectation position squared, then it will be, and then make another averaging. It will be a good measure. It will be a definition of standard deviation. If one is opening the bracket, it will be like average squared minus 2 x, x, another average minus x squared average. And this operation includes average over x, which will give 0. And then the result will be every expectation value of position squared minus square of position expectation value. Did you saw this equation before for standard deviation? You may have. Probably, yeah. So STD, standard deviation. But you see, it's direct. It's the same thing. So we do need this thing for the following purpose. The wave packets sometimes experience no change in their position, but they become more skinny or more fatter. So we saw this as an example. If you set up 0 initial momentum, but free space, no potential, it will expand, right? So let's maybe do this experiment first and then go further with formulas. I know that I'm delaying the whole process substantially, but there is no reason to go forward if we do not agree on basics. Okay, so sharing screen once again and inviting everyone to do the same manipulations as I do. So we go to the line number 5 and we change P naught to 0, which means we assign no initial momentum. Then I save and either put green triangle to run, or in the command line, I'm typing the name of the code. So I need to rerun it once again because it was too quick. So here is initial distribution. Then I hit enter. And you see, as time goes by, it doesn't move left or right, but it becomes more dispersed, right? So we need an observable. We would not identify this motion if we describe our research on the language only of expectation value of positional momentum. Neither position nor momentum are changing, but there is an explicit dynamics, right? So we need some additional observable measurement to speak about it. And among this self-printed observables, there is this sigma x, which is our width. And you see it grows quadratically, right? Same as we predicted years ago, months ago, right? There is method 1, method 2, and dashed line is what is predicted from theory. So it goes along with prediction. But how do we compute this width based on numerical data? Let's go into the code once once again. And I'm going to focus your attention on a specific line. Okay, this one would be okay. Line 209 and 210. So you see, we have independent variable grid point of x minus, so AVG3 is expectation value of position. Then it is taken squared, and then it's multiplied by probability. And this summation replaces integration. Do you see analogy with this, what is written here, right? So if I believe this equation, I may want to check that it is what I am expecting in the figure once again. And oh, what do I forget? It's there, but I didn't verbalize it explicitly. The line 209 variance 3 is only one value along the trajectory, and we need to accumulate. 15, yes, correct, thank you, 215. So variance is 3. So we need to, there is difference in these variables only in the letter S, but we need to accumulate all data along trajectory. So in the command line, I should plot variance 3. And then I see this line that looks quadratic, right? And it starts not from 0 but from the initial value. Okay, so please try doing this exercise, and I'll make a quick tour around. Okay, excellent. Yes, super.
Zero, right? Like you would think it wouldn't be moving anywhere or doing anything, but as time goes on, the probability of it being in a different position expands, right? And
Yeah, correct. Yeah, thank you. So let's quickly go over online attendees, just to make sure that we are all on the same page. Alison, would you please share your screen? And did you get this quadratic function as?
Sorry, I missed the was it plot variance?
Yes, plot variances 3. Plot variances.
Is there an S?
Yes, at the end, variances 3. Close the bracket. Yes, perfect. Yeah, thank you. You can stop sharing. Sibel, would you please share screen? Excellent. You can stop sharing. Joshua, would you please share screen? Excellent. Thank you. You can stop sharing. Lola, would you like to share screen? Okay. Yes, I see it. Excellent. Thank you. You can stop sharing. So what is our next little thing? There is also, you see, expectation value of momentum squared, and there is a expectation value of variance of momentum. And by doing expectation values of momentum, one also uses this normalization just in case to trust the results. And but it follows the same protocol. So accumulation expectation values into array of data for the whole trajectory. Saving numerical data into files for separate analysis. So if you hate MATLAB but love Microsoft Excel or Origin, this would be a question to you. Oh, and we already done computation of expectation value, position of and momentum. So numerical data into file separate analysis. Let's look through the I'll better show it on different equipment. Share screen, desktop, share. So after the cycle, the loop over time steps is done. There are several commands for plotting this stuff, but let's look for save command. So we during previous presentation we saw a use of save. There's only this one, var theory. Let's check if other variables are saved. Okay, it is not there, but we can immediately practice it. So, for example, the variable of interest was variance S3, and we can just save it. And if I type ls, it shows ls v star. It shows all files that starts with letter v. So it has this variance S3. And there is I can open Excel and read this file, or I can just maybe open it in file browser. Go downloads variances. So it's just data file, but I can open any of the data that were saved and import this data into other software. So it can be also imported into the Excel. Do you want me to speak more, or it is kind of simple thing that everyone can do? More or not? Okay, good. I'm happy to skip it because it's so boring. So what is our next next focus? So we've done expectation value of position and momentum. Uncertainty of position we also done, but there is another thing that we should cover: expectation value of energy. So why do we need it? Remember in class we were representing eigen states of particle in the box and oscillator as orbitals which are offset by energy, right? So it is not super scientific, but it appeals to human intuition, right? So you see that it has higher energy and oscillates at allowed higher amplitude if it's oscillator. So we may want to appeal to the same human intuition when working with more complicated systems, because if we change initial momentum, we also change kinetic and total energy. And by shifting the image of the wave packet by the value of total energy, really unleashes the intuitive interpretation by human brain. And let me give a truly physical chemistry example, which will appeal your brain and hearts as chemists. So did you hear about chemical reactions which are activated by heat? Right? It makes sense. Like you have a piece of paper, it exists. You start heating it, it starts burning, right? Activated by heat and many other things. So heating and preparing to facilitate reaction means increasing expectation value of total energy, of kinetic energy and total energy. And the idea that reaction doesn't go without heating means between reactant and product there is a barrier. So in order to come over the barrier, one needs to increase the energy. And if we, in what follows, want to quantify such processes, we need a language, we need tools to speak about expectation value of energy. Does it make sense? Enough as motivation? Okay. So let's have a look onto the line before the loop, maybe inside the loop as well. So (154), and let me check if it is recomputed along the. No, it is not. So the present version of the code, and probably should stop sharing just to make better focus on the blackboard. Stop sharing. Okay. So right now we plug here the Hamiltonian, which is kinetic plus potential, and kinetic is momentum squared over 2 mass, and potential will be a standalone operator, right? Present version of the code is based on belief that total energy operator doesn't change in time, and the expectation value doesn't change in time as well. Later version of the codes will have situations when energy may change in time if you have external perturbations. But right now, it is computed not along the loop just once. So if we just plug in this stuff here instead of operator A, then there will be expectation value of energy. So Hamiltonian is encoded by variables hem, I think hem and hem2, hem3, not because of food, but because of the Hamiltonian. And those of us, I think it is will be not only Wyatt, but someone else who will remind us principles of wave packet propagation. We'll use this Hamiltonian operator in order to set up evolution operator as a matrix exponential of minus I Hem2 times tau, right? So Hamiltonian is needed for evolution. It's a core of our thing, but we also can find expectation value of Hamiltonian and see what its value. We will do this little experiment. Intuitively and approximately, the potential in this current setup is 0. And energy will be purely composed of kinetic energy. The expectation value computed with momentum squared will be somewhat different from kinetic energy computed in a classical way, but by the order of magnitude, but as an approximate estimate, it will be close. So the result of this operation should be approximately equal to P naught squared divided by 2 mass. So if we have more than average curiosity, we can do this little experiment. So let me share screen once again. Share MATLAB. So it was a place right before, yes, line 154, E2 and E3. So the energy, total energy by method 2 and method 3. If I just type E2 and E3, it will be result of quantum computation of expectation value of energy. If I take P naught square divide by 2 divided by mass. Here I did set up the momentum 0, right? And now we see that even with 0 momentum, there are some quantum corrections. So it's not ideally, but if we go to higher value of momentum, you'll see that the quantum value will increase as well. So just try typing this E2 and E3. I think it is not worth of checking that you can easily do it. And there is an important specifics and feature. So even if we believe that wave function is normalized, it doesn't hurt to renormalize it once again. So divide this expectation value definition onto normalization factor, which can be computed right away. Without this thing, there could appear doubts in the value of results. Later on, during the propagation along the trajectory, numerical error may accumulate and violate the normalization. So if we redo normalization, it's just good style. It's not part of the code, it's just programming trick. Okay, let's check what is next in on our agenda. Stop sharing here, start sharing there. So we are done accumulation of expectation values, saving numerical data, position and momentum done, energy, uncertainty of position done. Okay, let's go to visualize real and imaginary part of wave packet. So we are doing, if we are presenting on the November 5th, then we will have one more meeting before that. So even if we do not cover the whole list today, we can tie the loose ends in a week, right? And next time we'll go quicker, just making sure that everyone is on the same page. In the remaining things, most challenging is this one, commutation. And it is not hard to implement. It's hard to explain what is going on. So thank you, Joshua, for selecting. I applaud you, how brave you are. Okay, let's focus on visualize real and imaginary part of the wave packet. So I'll speak a little bit more just as a small motivation, and then we'll go to details. When we started these labs, we did some demonstration of spirals, right? You remember when there are real and imaginary part of the wave function. And I have positive memories about the times, but those exercises were bound to, even if today we will consider particle without box, without any potential. In the past, we considered very narrow-minded analytical solution. We just illustrated the formula, right? And now we have a universal tool that would be able to generate wave function at any time for any one-dimensional potential. So we are doing much more universal time. In some sense, we want to see this three-dimensional spiral once again, but match this former spiral to the language of the code that we are working on today. Make sense? So why this spiral is popping up? What is going on there? I have clear mind, but just I think it will be a little more vivid if we have a little interview. I don't know what I'm doing. So, Nate, would you please share your vision? Why spiral is three-dimensional spiral is appearing when we speak about wave function?
Well, I know it represents the real and imaginary parts.
Okay, good. Wave function has a real and imaginary part. Yeah, good. What does imaginary part of wave function corresponds to? How to just wrap our minds around it?
The imaginary part. Could you attribute it to like trigonometric kind of
Yes. So it's a trap. It is a tricky question. There is no like direct question and answer. It's maybe associations. Yes, trigonometric functions, but then we designed the theory to predict probability distribution, and it is possible only if we use concept of this action accumulation of phase, and we fail to do it otherwise rather than putting the action into phase of imaginary exponential. So basically, the quicker the particle is moving, the more dense are the fringes, and fringes kind of migrate between real and imaginary domain. Is it something that would be close to your thoughts?
No, but so the imaginary is on the fringes and on the edges of where we're trying to find our expectation values. We're only trying to find the real, but the imaginary show up just because it's on like the outer edges.
Yes, I wouldn't express it this way, but nothing was wrong. So here is a less philosophical way. The Schrodinger time-dependent Schrodinger equation includes imaginary unit. If we integrate it, this imaginary unit will pop up into the power of exponential. And if the solution is imaginary exponential, it will naturally have real and imaginary parts. Okay, so at least we agree with each other with that. So Joe, what is your vision why there should be imaginary part of the wave function? By your own words, and you can smile to the camera if you want.
I'm not entirely sure, but I think it's more, it has like more to do of like kind of like depending on it, kind of like how it kind of like sets or allows it to be like converted between like different bases, I guess, or bases. I'm not entirely sure.
Okay. So plane wave basis naturally has imaginary part, and expansion coefficients may get imaginary. Yeah, it's not wrong. I like this idea. So anyone on the online wants to share ideas, please speak. And if you don't, I'm fine. We will just save time. Okay, so let's focus back on this blackboard. Okay, I'll draw something that this is a little delay, but I think everyone don't mind. So it is kind of a review of what we did through the semester. So we started the course with an idea that we as particle is moving along certain trajectory, it accumulates action. The particles demonstrate oscillatory behavior, and the phase of these oscillations come from this action. On one hand, the quicker moving the particle, the more dense are the fringes. So it's a more philosophical way. A little bit more practical. If we already believe that that there is a time-dependent Schrodinger equation, so we function changes in time according to this equation, then this imaginary unit will immediately pop up into the solution, right? So if we integrate left and right part, you'll see that psi will be psi at 0, and it's just more logical to put, say, not here, and here we do E, maybe T naught. Here we have T naught plus delta T. Right. So this exponential, imaginary exponential has real and imaginary part. And at any time step, even if the original wave function was completely real, it will, through time evolution, it will get some imaginary components. So it's just the theory of quantum mechanics is formulated this way. And so it's maybe was one way to think about it. Second one. And the third one, if our wave function at time zero can be proportional, something times E minus I momentum h bar x, if it has non-zero momentum, if it is related to plane wave, then it naturally has fringes. The higher the momentum, more denser fringes, and these fringes come both to real and imaginary domain. Make sense? More or less. Okay. So we are going to illustrate all these concepts together with just plotting wave function, maybe at initial and final, times. Screen. Command line. Okay, so if I browse through the code, I see this psi2 and psi3, which current version of the wave function. Psi3 equal psi. So I scroll backwards, and in the line 66, I have the initial wave function psi naught at initial time. So we intentionally design it as a Gaussian wave function, so quadratic with certain initial variance centered at x naught, and we multiply it by plane wave p naught times x minus x naught. Let's plot this function first and then see how it changes over time. So figure, and then I want, if I do plot psi naught, I expect to see some noise. So it has only real. Let's try real. It is the same. And if I try imaginary, it shows 0. So it agrees with the fact that we intentionally set up initial momentum p naught equals to 0. So it's quite boring and we do not see any fringes. So if I modify the code and return some non-zero value of momentum, so I save and run. Moves. Approaches and reappears. And let me close everything, open new figure. And then I will do the same exercise as before. So plot psi naught. Do you like it? Can you interpret what is shown? At least it's something different, right? Right. What if we do plot 3 x uppercase x, comma psi naught. It doesn't want real psi naught, comma imaginary psi naught, psi naught. Do you recognize your old acquaintance? So, do you? Does anyone feels happy and recognizes this image, or it's completely new and you do not? Yeah, thank you. Wyatt?
It's like that one from a different lab that we did, right?
Exactly. So we plot both real and imaginary, and we see that they both are play their role. So the wave function has oscillations when real converts into imaginary, but they're defined only in the vicinity of this grid point 30, right? As we go away, they exponentially decay. And these fringes correspond to the fact that momentum is non-zero. So when momentum was 0, this image was given nothing. Let me rerun the code figure. I will do another example. You don't need to repeat it. If I return to the small value of momentum, like p equals 0.25, save, run. And now I can, yeah, close. And now I'm trying to run the same command. So it is initial wave function p naught for the momentum value equals 0.25. So let me bring two figures together. So on one figure we have this corresponds to initial momentum p equals 0.25, and here is 5 times bigger, 1.25. You see it, there are more cycles per unit length. It corresponds to higher momentum, right? What else? Let me maybe do one more thing, and then I'll make a tour over the seats. So figure. So if I plot not psi naught but psi 3, which will be wave function at the end of the trajectory. So this one is not analytical formula. It's results of simulation, and it shows wave function that has slightly propagated from the left to the right. And you see the fringes of the front and back have different density. It's like a chirping pulse with offset between nearby coil changes, right? Because more quicker component departs further, slower component stays behind. Therefore, it shows coils with different densities. And when we were doing our regular analysis, which is plotted without the special commands, once again, we are plotting X probe 3. Probe 3. Okay, let's do. Oh no, it's just this one. Probe 3. So here is the wave function at the final stage of evolution as we computed here. And the probability distribution is quite boring. It just shows where the center and what is the width of the distribution. But there is much more additional information hidden in the wave function. So if you plot not probability distribution, but wave function itself with real and imaginary, we see that it contains additional evolution about phase, about how the momentum of the forerunning parts is higher, backward parts are lower, and it's beautiful concept, beautiful image, but in typical experiments, it's not measurable. It's more like abstract concept, which is very helpful in predicting outcomes of experiment when we apply the concept of expectation value. So if we want to publish a paper with comparison to experiment, we probably should stay away from plotting wave functions. We should plot expectation values. But if you want just to impress mathematicians or theoreticians, we should plot wave function and praise how beautiful it is. So please try to plot maybe just this image of the wave function at the last stage of the evolution. So this one, real and imaginary. And I will make a tour over seats. Okay, can you rotate it? Oh, yes, beautiful. Thank you. It looks like cover for a lamp in a fancy apartment. Okay, excellent. Probability? Okay, yeah, thank you. Yeah, I see, I see. And you can arrow up to avoid unnecessary typing. Okay.
No, the one.
Probability distribution. So plot
Oh yeah.
without 3, plot X, probe 3. Okay, yeah, thank you. So I'm going to ask those who are online to share screen one by one. And we will stop in 8 minutes to stay on time. Oh, okay, I see someone is already leaving. So, Sibel, would you please share screen? Okay, this is at the beginning of the evolution. And can you show image at the end of the evolution? If you bring, instead of psi naught in your command line, replace psi naught to psi 3. Yeah, it is beautiful. Do you have any comments or questions about this image? Or it looks natural to you?
It looks good.
Okay, yeah, thank you. It would be good decoration to make like printed on 3D printer.
Yeah, yeah, it's a nice spiral.
Okay, yeah. Would you please? Oh, okay, that's fine. Next, Joshua, would you please share screen? Okay, yeah, I see all of them. Yes. Yeah, this is good. Can you? Yes. Yeah, nice spiral. Okay, and probability distribution. I saw you made it. That's beautiful. Yeah, thank you. You can stop sharing. Lola, would you like to share screen? Okay, yeah, I see them both. Excellent. Yeah, thank you. You can stop sharing. So I wonder if you have time for anything else, or it's good time to wrap up. So visualize real and imaginary parts of wave function. Potential and probability distribution. Why there are 3 of them? Visualize any observable bundling. I think it would be more natural if we just finish now. Are there any objections? Okay, I think we did 2/3 or more than 2/3, and then we will do the rest on coming Wednesday. And the one who selected applications last subject, I don't remember, Nate. Okay, so a week ago I was sending several versions of the code. This one is called like WP wave packet free for free space, and there were versions of VPHO for harmonic oscillator and VP box, something like that. They are pre-made for particle in the box and harmonic oscillator, and you can inspect them. But right now we're not going to do it, but it is just one line change between this code. So it's really easy to modify potential. It's just changing variable V at the beginning of the code. But let's announce adjourn. So meeting is done. Recordings will be distributed like after midnight. Hopefully I'll stay here to answer any questions, but everyone is welcome to disconnect and depart. Lola, did you have questions to discuss?
What about my research?
Huh?
I said yes, but it's about my research.
Okay,